So welcome to ECEN 215, Principles of Electrical Engineering. Today we are going to talk about Kirchhoff's laws. This is a very fundamental topic and is the basis for everything else we're going to be learning in this class. So this is an incredibly important lecture. It is relatively short because the concepts are pretty basic, but all of the analysis techniques that you're going to see moving forward is based upon these two laws that we're going to discuss. So let's just go ahead and get started. So we're going to first go over what we call the current law and the voltage law, Kirchhoff's current law and Kirchhoff's voltage law, which is for the next several weeks, and honestly for most of the semester, is the basis for the class. These two laws that you're learning here are going to determine all of your equations that you're going to be working on for the rest of the semester. And go back to what we learned in the very first lecture about the conservation of charge. So in this case, Kirchhoff's current law is really simple. The net current entering a node, and we define a node as a point where two circuit elements or multiple circuit elements meet, is zero, meaning the node itself does not hold charge. It is just a conducting point. So we have a circuit element here, we have another circuit element. In this case, in part A, we have 3 circuit elements. B, we have 2 circuit elements, and C, we have 3 circuit elements. So we've arbitrarily have defined, just like we learned earlier, we arbitrarily have defined I1 is current going this direction, I3 is current going this direction, and I2 is current going this direction. Using KCL, Kirchhoff's current law, we're able to actually now write an equation. If we say minus I1 and minus I2 is plus I3 equals 0. Now the important thing is like, well, why minus? Well, it depends on what you consider the direction of way the arrow is entering the node. So you've arbitrarily defined you either enter or leave a node. So in this case, leaving a node is considered a positive current, and current entering a node is considered negative current. So I3 is equal to minus I1 plus minus I2 plus I3. So leaving and then entering and entering is equal to 0. You could rewrite this simply I3 is equal to I2 plus I1, which if you look at this, you can agree with that. If this current is entering here and this current is entering here and it's leaving as I3, then clearly I3 is equal to I1 plus I2 because the node itself cannot conserve current. And then we have the same thing going on here. We have node 3 and current 3 and current 4 and one node here, B. Well, current leaving, we're going to leave as positive, so I4 plus negative I3 must equal 0. In other words, I4 is equal to I3. And then here we have, 3 currents entering a node. So all 3 are entering. So we have minus I5 plus minus I7 plus minus I6 equal to 0. And again, just simplified, I3 is equal to I1 plus I2, I4 is equal to I3, and then I5 is equal to minus I6 plus minus I7. So this is very important. As simple as this might seem to some of you, definitely this area will trip you up. When I've taught this class over the last several semesters, this is probably the #1 area where students, if something mathematically goes wrong with your equation setup and doing a circuit analysis, it's because you're not following this convention. I always personally, I like to do current leaving a node as positive and current entering a node as negative. That makes setting up these equations I mean, technically you could do it the other way around. You could say that any current entering a node is negative, and then all current entering a node is positive, and all current leaving the node is negative. Mathematically, you would end up at the same thing. The key thing here is you must maintain that convention. Whatever convention you use, it must always be the same. You cannot swap conventions. You can't do half of a circuit analysis with I3 in this case being positive and I2 and I1 being negative, and then come over and do another part of the circuit where you flip-flop it. You must always decide entering a nodes are negative, leaving a node is positive, and then vice versa. You must pick one direction. So just following in that, we have circuit elements A, B, and C here with nodes 1 and 2. In this case, IA is equal to IB equal to IC because there is nothing being held for current conservation in nodes 1 and node 2. So simply, this is all one current. Looking at this circuit here, we've got circuit elements A, B, C, D, and E, and we've labeled IA this way, IB going out this node, IC going this. So what can we do here? Well, we have IA, so if we were asked, what is the equation for this node here? So let's think about that for a moment. Like I said, the convention is I like to use leaving as positive. So we have IB minus IC minus IA is equal to 0 for this node. And then looking at this node here, where everything connects, so we have circuit elements B, E, and D connected together, so this node. And again, same convention, leaving is positive, entering is negative. We have minus IE, minus IB, minus ID equal to 0. So IB is equal to IA plus IC. And then we have ID is equal to minus IB minus IE. Now is the other Kirchhoff law. So like I said, that was half of the major point of this class is understanding Kirchhoff's current and then understanding Kirchhoff's voltage law. So KVL here states that the sum of the voltage is equal to 0 for any closed path in an electrical circuit. What that means is if we've got a path here where we have a complete circuit, where you complete a loop, if you will, we have circuit elements A, B, and C here, and we determine a loop. If you notice, we call this loop current 1, I. And in this case, we're showing it going, in this case, clockwise direction current. So the current going through B from minus the positive. Here it's entering the positive VA, entering A and leaving, and then going through C. And so we're doing this loop constantly. So kind of going back to the very first slide we had earlier about one of the first slides where we're talking about energy absorption, energy supplying. If the current was going in the positive, this is absorbing. The current here is absorbing. So if VA is truly positive and VC is positive and VB is positive, assuming everything is positive here, right? Then this element here, by the way, would be a generator because you notice the current is going in the negative terminal, but the other ones it's coming into the positive terminal. So that's, kind of going back to that slide we had earlier. So let's just take a look here. So we have current loop 1. What are we saying is that the voltage VB, so we have to add all these voltages up. We have VB, VA, and VC, that the voltage in this loop must equal 0. So if you're using convention and we go in the positive terminal, so VA plus VC, so every time you follow I, you follow the current, the head of the current, if you will, the arrow, we come in VA plus VC, so we're following the symbol, plus VC, but here we enter on the negative, so minus VB is equal to 0. So just to kind of put finer point on that, when you're moving from plus to minus, we add. So simply if the current is going through into the positive terminal, leaving the negative terminal, we add the voltages. And when we enter the current entering the negative terminal to the positive terminal, then we subtract. Again, this is seems simple, but this is where a lot of mistakes are made. You just simply stop, take your time, look at the circuit element. If the current is entering the negative, you subtract. If it's entering the positive, you add. So going back to that little circuit we were just looking at, let's just write the equations here. So we have minus VB because we entered here. So minus VB plus VA plus VC must equal 0 by Kirchhoff's voltage law. In other words, VB is equal to VA plus VC. So now we've kind of do that. Let's kind of take a little side trip here and talk about a thing called parallel circuits. So we have circuit elements VA and B, And we have circuits elements D, E, and F. And now these could be any type of elements. Like I said, it could be resistors, which is what we're going to start with initially in this class, analyzing. It could be inductors, capacitors, it could be diodes, it doesn't matter. The voltage across element B is the exact same voltage across element A because they're connected together. They are wired together. So they're sharing the same node. So element VA, the voltage across, if this was positive here and this was negative here, and the VA value is equal and is the same as VB. This would be VC from this node to this node, and the voltage across VD is this voltage if this was positive here. In fact, let me draw a little, get the little pen. So if we labeled this positive and negative, and this is positive, negative, and I labeled this positive, negative, I decide as the certain person doing the analysis which one these are. And I determined all these to be positive and negative like this. And that was my decision. Then what do we end up with? Then we end up with VA, VB, VC, VD, V, and F. So VD, E, and F are all the same because they're all the same voltage. VC, switch this back to the laser pointer. So VA and VB are the same. VD, E, and F are the same, and then VC is on its own. So we have that. So kind of taking a look at this circuit again, VAB, VC. So here we have two separate loops here. We have loop 1 and we have loop 2. And so we can write an equation, and of course there's also one master loop here, loop 3. So we look at loop 1 here, we have VA plus VB, or VA is equal to VB plus VC, because remember we entered the negative terminal here, we're in positive terminal, positive terminal. So this loop here is governed by this equation because of Kirchhoff's voltage law. Here on loop 2, it's kind of similar, except now it's VC is equal to, this one's a little different though. We're entering negative. So we enter the negative here, we enter the negative here, but we enter the positive here. So we end up with a little different equation, as VC is equal to minus VD plus VE. It's again, very important you pay attention to what arbitrary plus and minus and arrows that you've got for currents. So again, mathematically, we're using the Kirchhoff's current law and voltage law to set this, but that's what determines what's going to go on here. So in summary, today we talked about Kirchhoff's voltage and current laws. And again, this is a very fundamental lecture, and I would recommend if you ever get lost in any of the ongoing lectures when we start getting into circuit analysis methods that is shortly upcoming, that you come back to this lecture and especially understand the concept of Kirchhoff's current law, that the sum net current in a node must always equal 0. There is no charge left inside a node. That the sum of the currents entering a node must equal the sum of the currents leaving the node. And that is a very important thing. There's various methods that we're going to be exploring that, but in the end, Kirchhoff's current law must be obeyed, and at the same time, Kirchhoff's voltage law must be obeyed. And both these laws happen simultaneously. And we're going to have methods that we are going to focus on the current law. We're going to have methods that focus on the voltage law. But in the end, you can swap back and forth the methods. And in the end, both laws are being obeyed simultaneously in a circuit at all times. So Kirchhoff's voltage law, again, in summary, is that in a loop path in a circuit, and it could be any loop path, if you add up the individual voltage drops across any element, and arbitrarily you determine, the VA, VB, VC, whatever it is, based upon your plus and minuses that you assign, the equations based upon those assignments must be in a circuit loop must be equal to 0. So again, current law, the net current through a node must be 0. All current entering must leave. In the end, there is no current left inside an individual node. And a node, again, is any circuit elements that are connected together. So if you've got 10 circuit elements that are all connected together, then there is just one node that connects them. Now you could draw it as a bunch of little separate dots so that it, visually you don't have a mass of 10 things connected to one point. But electrically, it is 10 things connected to one specific node. And that's, again, important to realize. You don't have to write a set of an equation for each individual dot. It is only the one node which connects all the elements. Same thing's true with Kirchhoff's voltage law. So hopefully you found this lecture interesting, and again, it's very fundamental to this class. If you have any questions, please make sure you come to the office hours and or to the Q&A and start asking those questions in this class. Again, the Q&A period is critical for you to ask those questions, interact with some of the problems, and get a fundamental understanding on these principles.